Hi everybody, I'm Dana Downs. And I'm Jessica Whiteaker, and this summer I got to play with those. Okay, so now many change sea level is on the rise. So how are they going to find solutions for this problem? The dynamic presentation. Here we go. Okay, musical mics. All right, so all right, so your side of the stage. Horrible, I'm so sorry. Here, you guys just possibly share one. All right, much better. So how is NASA going to prepare for the imminent flood? The first step in finding a solution to any problem is to gather data. So they asked UNAVCO and the University of Colorado to make some 3D models with, of their facilities with terrestrial laser scanning technology. So from now on, we'll just call it TLS. So up here, you see a 3D image of the Ames Research Center in California. Very colorful. Those colors represent elevation changes. They can combine this data with GPS data and kind of make a plan. They'll know which areas are most vulnerable to sea level change. All right. So, sorry, how do I go back? There we go. So why use TLS instead of traditional surveying methods? Well, this little animation here, which was created by one of our mentors, Keith Williams, displays that very nicely. Yeah, there is an immense amount of data that can be collected and stored in a very short amount of time. So how does TLS work?
Okay. The terrestrial laser scanners, they sit on top of tripods as shown in the picture to the left. And the way they work is that they send out a pulsating beam of light that then hits an object and is reflected back to the scanner. The scanner is able to pinpoint where the light reflects it by knowing the speed of light and the angle at which it left the scanner and the angle it returns to the scanner. In a single scan, the scanner is picking up millions of these points that it then organizes into a 3D image, like this one on the left of the Kennedy Space Center Launchpad. And the way that Keith Williams was able to create this image was he scanned from multiple positions and then tied the scans together. However, as useful as TLS is, there is a problem with it. As the distance between the scanner and the area being scanned increases, the spot size increases as well, or the diameter of the beam. This is similar to if you shine a flashlight at the ground, the area of illumination is small, whereas if you shine a flashlight off to a distant wall, the area of illumination grows larger.
Okay, so this divergence of light can seriously affect the image that is produced. For every beam that's sent out, only 1 point is collected. So for a shorter range, let's say 100 meters, the area detected is about a 3.5 centimeter circle. So you move out further away, and you have this giant area at 900 meters. It's about 35 centimeters, which could be larger than the target, and still you're only getting 1 point of return. So this explains why a point cloud from a 100-meter scan looks pretty good, and it varies so much from the one on the left, which is at 900 meters.
The manufacturers of most scanners only give us accuracy and precision ratings out to 100 meters. For example, the VZ-400 scanner has an accuracy of 5 millimeters and a precision of 3 millimeters at 100 meters. The problem with this is that scientists are often using these scanners at distances that are far greater than 100 meters, and they need to be able to know the exact error to be able to account for it when they're conducting their research.
Okay, let's do a quick review of accuracy and precision. So imagine that the bullseye there in the center is your true value, the one that you're looking for. And your measurements on the left-hand side, they all come pretty close to that target value, but not necessarily to each other. That is accuracy. If your points, however, are not close to your target value, but they're clustered together, they're very close to each other, then that demonstrates precision. We're looking for both of those.
Okay, so to be able to determine the accuracy and precision of the VZ-400 scanner, we set up an experiment. The first step we had to take was to create a target that would be large enough for the scanner to be able to pick up. So we made a target that was 25.7 centimeters in diameter. It was a perfectly flat plate, and we covered it in red reflective tape.
One of the neatest parts about our target was the apparatus that it was mounted on. So this was a lead screw machine that allowed us to move our target left and right and forward and backward very precisely, very accurately to the millimeter. So we scanned our target, then we moved it to the left 1 centimeter, or we scanned our target 5 times, and then we moved it over, and we did the same thing. There was a total of 11 centimeters for each test, or 10 centimeters, 11 positions, sorry, for each test. And then we turned our target around the other way and tested the range. So at our field site, we picked a large area that was completely flat. We wanted to make sure that there was a direct line of sight between the scanner and our target, and that line of sight would be parallel to the ground so as not to introduce any other variables into our experiment. So at first, we scanned at 100 meters. We performed both the side-to-side and forward and back tests. And then we went out to 300 meters, 500, 700, and finally 900 meters. So in total, we scanned 550 times. We were out there about 3 weeks in the field, right next to the mountains, so we didn't mind. Yeah, that didn't even include all of our preliminary research. So.
Okay. The first set of results we're going to show you are precision results. In all of our graphs in the bottom right-hand corner is a legend saying which axis we moved it in. On all of our graphs also, the blue line is X, range. The orange line is Y, horizontal. The green line is Z. The green line is Z, vertical, and the purple line is the 3D, which is the sum of those three. In this graph, we moved our target left to right a total of 10 centimeters for horizontal precision. And what we have graphed on our y-axis is the standard deviation of the values of the points that the scanner gave us from each other. And as you can see, as the distance increases, so does the standard deviation of the points from each other in the horizontal axis.
Okay, this graph is just like the last one, except this was when we manipulated the range of the target. So not quite as conclusive of results as the last one. You can see that there is an upward trend for both the horizontal movement of the target and the vertical displacement. But there's that giant spike there at 700. That particular day, we were along a dirt road, and there were trucks that were, barreling through there. So there were these giant dust clouds, and yeah, it's kind of hard to control for that. All right, but you will notice that the range there, it tends to stay pretty consistent. So this is a zoomed-in version of the range, and you'll see that it's only about a millimeter off, which is excellent. That is due to the way that the scanner finds the range. Rather than having to deal with the spot size and the mirror calibration and how the scanner turns, which affects both the X and the Z coordinates, it is only dependent upon the light leaving the scanner, hitting the target, and returning.
Okay, this is a graph of our accuracy. The way we determined the accuracy was we would scan our target 5 times, then find the average of that, and then we would move our target over a centimeter, scan it 5 more times, and find that average, and then we would see what distance that the scanner saw the target move. We did this for all 10 centimeters, and what we have graphed here on the y-axis is how far the scanner was off from that 1 centimeter mark. As you can see, as the distance increases, so does the error in the horizontal, while in the X, or the range, it stays relatively constant. This is a graph of our Z vertical axis at 1 scan position. The scanner picked up 20 centimeters of variation, even though we did not move our target at all in the vertical axis. You can notice that most of the variation is in the first few scans, while in the last scans it seems to level off. We think it would be wise for researchers when they're performing research to take several preliminary scans before taking scans that they'll actually use in their work.
Okay, so we have a few conclusions. Qualitatively, the scanners performed as we thought they would. It seemed like accuracy and precision, at least in the y-axis and in the vertical z-axis, they did decrease with time, or with distance, excuse me. Though we do have insufficient data to really identify a trend and to give some good quantitative numbers. We also know that environmental factors can play a huge role in the quality of the data that you can get. And also, yeah, that little bit of advice to field engineers, do those couple of scans before you set into your true data collection. Okay. For future research, we think that there should be more research done on the vertical axis and why there's so much variation between the scans. Also, to better determine the accuracy, the use of a total station, which would give the exact position of the target rather than us just moving the target and going off of how far we moved it to determine accuracy would give us better data. And if someone were to replicate this research, if they could find an area where they could eliminate some of the environmental factors that we encountered. Okay, we just want to say thank you to everyone who made this internship possible, and hopefully our research and what it leads to will help you out someday. Thanks.
Okay, so we're going to turn one of these on.
All right, do we have,
Oh, dear.
any questions?
Any questions?
Could you put the graph up that showed, as you moved the scan, what the accuracy was? Because it looked to me like it was 4 centimeters over a 10 centimeter change. Is that, am I misreading that? My eyes aren't very good.
It was, actually, this is how far off. So we moved it the centimeter, and we saw how far the scanner had seen it move. And then we found the average for all 10 centimeters at each scan position. So this is the average distance that it was off from the 1 centimeter. So at the 700 meters, it was off at 4 centimeters. So the scanner saw it move 5 centimeters versus where it only moved 1 centimeter.
Right. Okay. I find this very disturbing.
So this was at a test that was clear out at the 700 meter mark, but this particular scanner, the VZ-400, is only rated for use up to 500 meters out. So it's not being used in the field at that distance, typically. The spot size at which distance? 900 meters? Yeah, it's 35 centimeters in diameter. So that's pretty big.
So you only get 1 point for 35 centimeter diameter?
Yeah. So we are able to get a little clearer picture.
10% of the area of the spot size. 10%. The error is 10% of the spot size.
You'd said that you'd covered your target in a reflective tape. Is that something that's easier for these devices to see than they might typically be used on a building or whatever you might want to measure?
Yes, it does make it easier. In fact, if we didn't have the red reflective tape on it, we probably wouldn't have even been able to see it at the 900 meters.
So I have one with respect to that spike. I think you guys are talking about the dust interaction. So at 700 meters, is it related to the spot size and the diameter of the dust, or is it just strictly the wavelength of the light itself? Can you speak on that? If you do think it's the dust, what is the relationship between either the spot size at 700 meters, where the dust cloud was, or the wavelength of the laser?
I think it's probably the combination of both of them. That I think the line probably, because still at 900 meters, it's also very high. But I think the spike that you see at 700 meters that puts it higher than 900 meters is due to the dust. But it's probably also very inaccurate at 700 meters as well.
And yeah, the dust cloud is probably just, for every little piece of dust, it's going to, if there's enough of it in the area, it's going to send back a return as well at a different distance.
All right, so we've got a break until 10:15. Thank you, ladies. Excellent job.